Well, thank you, Mr. Chairman. Thank you, Phil. I'd like to thank ISSMGE and TC209. It's really a great honor to present this lecture on behalf of all my co-authors. I'm turning 60 in 3 days, actually, so you've given me a wonderful early birthday present. And I would also like to thank my family for their unwavering support. My son couldn't be here tonight, but my wife and my daughter are here. And believe it or not, it is their second ISFOG conference. My daughter Isabel was 1 year old when she flew all the way to Perth, Australia in 2005 to attend the first ISFOG conference. So what can I say? You got to start them young, right? So when I look back at my career, I realize how lucky I've been. You can see here a partial listing of the API Geotechnical Resource Group from October 1993. And here I was sitting 2 months in my career, sitting in meetings with Don Murph, Alan Young, Mark Randolph, and Suzanne Lacasse, who would all go on to be Terzaghi and/or Rankin and/or McClelland Lecture. So it was really a wonderful learning opportunity. I've never worked with Mr. McClelland. It was a little bit before my time, but I'm proud to say I've worked closely with all the previous six McClelland lecturers. Don I met in 1990, as Phil mentioned, so tonight actually makes Don the first member of a very exclusive club, which is the people that got the McClelland Lecture and whose student got the McClelland Lecture. Mark and Alan I met in 1993, as I just explained. Knut I met in 1994 when he was leading a joint industry project on the design of suction piles. Ed I met in 1998 when he joined Amoco, just 1 week before the merger with BP was announced. And Richard I met in 1999 when he joined the ISO resource group on offshore geotechnics. So thank you all, gentlemen. It's been a pleasure working and learning from you over all those decades. So what it is that we do as geotechnical engineers and what is our goal? In chronological order, what we do is we go in the field and we do geotechnical and geophysical site investigation. We characterize the sites and we take soil samples. And then we take those soil samples and we bring them to the lab and we measure the soil properties that are of relevance to our project, to our problem. And with those soil properties, we run numerical and analytical models to try to estimate the capacity of the foundation. And to verify and calibrate our design methods, we do physical testing, either in the centrifuge or at 1G, but rarely, if ever, full-size foundations with full-size loads. So all those topics have been covered in great details with the previous McClelland lectures. And there are proxies to what we really are trying to do, which is predict the field performance of the seafloor and full-size foundations under full-size loads. So a fair question is, how well are we doing? So through the lecture, I will take you through some case histories to show you that overall, we're doing very well if we follow the latest recommendations in our offshore codes and standards, although there are cases, as you will see, where we got it very wrong. So this is the content of the written version of the lecture. We will talk about submarine mass movements with anthropogenic or man-made triggers. We'll talk about the Valhall pile buckling incident, and we'll talk about the performance of anchors and piles during the accidental limit state under very large loads that are imposed by hurricanes for floating structures and fixed structures. And then we talk about the performance of foundations at the serviceability limit state. We talk about the Magnus Foundation Monitoring Program in the North Sea. And then we talk about the performance of foundations at the fatigue limit state under very, very small loads. We can't talk about everything tonight, so these are the topics we will concentrate on, but just so you know, there's more in the written version of the paper. So let's start with offshore geohazards and submarine mass movements. If you look at the open literature, you will find that it focuses almost entirely on natural triggers. Example of submarine mass movement with anthropogenic triggers are virtually non-existent. So in this lecture, I will walk you through two case records. And the first one has to do with our drilling activities. So you can see here a typical deepwater drilling system that is used in the shallow section of the well in the top, say, 1,000 meter of the well before the blowout preventer and the riser are installed. So the cuttings are circulated out of the hole by circulating mud in the drill pipe and returning the mud through the wellhead onto the seafloor. When the drilling is completed, the casing is lowered and cemented, and the cements are returned to the seafloor through discharge ports. So those volumes of cuttings and cement can be very large. As you can see here, the cuttings are being returned over the wellheads, and you can see here a cementing operation and the cements being returned onto the seafloor. So those cuttings and cement can be very thick. They can be up to 3 meters thick. So how do we know that? Well, we do bathymetry surveys pre and post drilling, and we compare the elevation of the seafloor, and the difference is the thickness of the cuttings. So you can see here this case records, all those dark blue dots are wells, and this is the thickness of the cuttings. So near the wellheads, you can see we have up to 3 meters of cuttings. And you can see that they can extend hundreds of meters away from the wellhead. You can also look at sub-bottom profiler records. You can see here a record pre-drilling and post-drilling. You can see the wellhead, and you can see again here 3 meters of cuttings near the wellhead. So question, can those piles of cuttings be so soft and so high that they become unstable? The answer is yes, and here's a case record. You can see here a debris flow that was triggered by the accumulation of soft cuttings over the wellheads, and the seafloor became unstable and the cuttings ran out 260 meters. We mapped the extent of the debris flow with what's called backscatter bathymetry data, and you can see here the debris flow is very visible. So locally, the slopes were up to 8 degrees, but you can see here it's a good idea to put subsea structures upslope of the wells, just in case you have one of those events. And we were fortunate, or unfortunate, I don't know, to capture the event live. So you can see here a world premiere of a deepwater submarine mass movement with anthropogenic trigger. You can see the drilling operation, and all of a sudden the seafloor becomes unstable, and the ROV is engulfed into the debris flow, which lasted about a couple of minutes, and like I said, ran out a couple of 100 meters. So if you slow down the video, you can actually, I find it very fascinating, you can actually see a cemented block intact that are being rafted over the debris flow. Here you can see the edge of a rafted block here that propagates onto the seafloor. Here's another one here. So very spectacular, and those events can occur. The second example comes from another deepwater area. You can see the seafloor rendering here, and at first casual glance, it looks like a lot of the seafloor we've seen before. You have a little bit of an escarpment, and yes, you have debris flow that have occurred, but there is a very unusual feature about this seafloor, and here it is. We have this linear scar that we mapped over a length of 4.3 kilometers, but clearly it extends outside the bounds of the survey. And it seems to be associated with 2 debris flows, which run out at least 2.9 kilometers. If you zoom in on this particular feature, you see that the linear scar exactly coincides with the head wall scarp of the debris flows. And we don't think that's a coincidence. We think the formation of the scar is what triggered the debris flow. And we believe that this scar is too straight to be the result of natural processes, and it's most probably of man-made nature. To give you an idea of scale, in this isometric view, you can see clearly the scar here, And you can see the scale of the scar. At point B, it's where it's at its widest and deepest, 13 meter wide by 3 meter deep. But you can see that the geometry varies along the scar. So that's an interesting feature that I had never seen in 32 years of experience. So the plot thickens because we have 3D exploration, low resolution bathymetry data from 2001, which strongly suggests, although we can't be 100% conclusive, that those two debris flows were not present in 2001, which makes them less than 24 years old. So what could it be that triggered those debris flows? Well, it could be the laying of a cable or a fiber optic line, but the scar is really too big and too wide for that. It could be the dragging of a survey sled during a deep tow survey, but again, the scar is too deep and too wide. And in the Gulf of Mexico, there were pipelines that were installed by being dragged along the seafloor, but those operations are very well documented, and they're all outside the area of interest, so that's not that either. Or it could be the dragging of a drilling rig anchor after the rig broke its mooring, lost position, and drifted during a hurricane. So I think we can eliminate the first three, and that's as much as I can connect those dots together for you. I will leave you to draw your own conclusions. So to summarize the bit about performance of the seafloor, we believe that case records of deep water mass movement with anthropogenic triggers are underrepresented in the open literature. They do exist. I've given you 2 examples, and I think we must have the courage to publish them. Again, they can be related to accumulation of drill cuttings or dragging of objects onto the seafloor. Now, I appreciate all those lessons were learned during the operations of oil and gas, hydrocarbons, but I do believe that they are applicable to new energy projects. For example, carbon capture projects can include the drilling of offshore wells to store the CO2, so you will have to deal with drill cuttings. Offshore floating winds, particularly in deep water, may have to lay a lot of cables on steep slopes with soft sediments. So you now have an example of what can happen during such activities. So now we will pivot and look at pile performance during installation with the Valhall pile refusal event of 2002. So the Valhall field is in the central North Sea. In the late 2000s, it included 6 bridge-linked platforms. So we started in 1982 with the quarter drilling and production compression platforms. We extended the field in 1996 with the wellhead platform, in 2002 with the injection platform, IP, and then in 2009. So we will talk about what happened when we installed the piles for the IP platform here. So for this part of the presentation, when I say we, I mean one or more individuals from one or more of the following entities: Aker Maritime, Aker Kværner, Aker Stord, Advanced Geomechanics, Arab Energy, BP Amoco, DNV, Fugro, GCG, GeoSurvey, Herema, Imperial College, NGI, NTNU, Rowan Drilling, Secor, Sintef, Saipem, UWA, and many individual consultants. And some of them are in this room tonight. So we can't acknowledge everybody individually, but we thank all those contributions globally. So within the foundation zone, the site has been affected by 2 glaciations. And in 1978, we took soil borings to design the first 3 platforms. And you can see the CPT records here. With the technology of the time, the cone resistance refused at as little as 37 MPa. The ground model is fairly simple. You have 3 geological units, the 4th formation, which is mainly dense to very dense sand. Underneath, you have the fissure formation with hard to very hard silty clays integrated with sands. And then you have the link bank formation, which is predominantly very hard clays. Now, when we designed the IP piles, we shot a geophysical survey, and I will show you one line here to try to see how uniform the conditions were at the site. So you can see this geophysical high-resolution line. You can see the 1978 borings, and what it showed is that the stratigraphy is fairly uniform and continuous across the site without buried channels. So we successfully used the 1978 data to design and install the WB piles in 1996, and we used the same data to design and install the IP piles in 2002. So you can see the design profiles, sands in the fourth formation, intubated sands in clay in the fissure, and clay in the link bank. Now, to calculate the SRD, the soil resistance to driving, we used the then new Almen-Amri 2001 method, which is CPT-based. And you can see the CPT record here that we had to input in the method to match what we observed at the WP platform. So this is the SRD that we measured at WP. We used the calibrated cone profile, and we predicted the range of SRD for IP. Those platforms are very close. The pile is the same diameter, so the range of SRD predictions for IP are pretty much what we measured for WP. Doesn't get any easier than that. We have a platform that was successfully installed just a few meters away. Well, you can see how physically those two close those two platforms are, and you can see WP, we installed piles successfully up to 63 meters. But when we came and installed the pile at the IP platform, 5 out of 8 refused between 13 and 23 meters short of penetration. So that was a big surprise, and you can see how the installation was aborted, the top side was not installed, the heavy lift barge was sent away, and that's how the IP platform was left in the field. Edge to edge, those two piles are just 4 meters away. How could it be that we successfully installed those piles with the same diameter, and we come back a few years later and we get in big trouble and we refuse those two piles here? So if you look at the SRD, you can see the ones in blue for the WP platform, that's non-refuse. And then you see the SRD for the piles that refused at this corner here. For some reason, in the fissure formation, you can see that the SRD starts to increase until it reaches about 130 MPa, and then the pile just refuses. How could that be? Why is that? So we recalibrated the Almen-Amri method to try to match what we had observed. So you can see here the SRD that we measured. This is our original prediction. So even the 2 out of 3 piles that did not refuse had SRD that were much higher than what we had calculated. So you can recalibrate Almen-Amri, and then, sure, you can match what you've observed, and here is our updated prediction post-refusal. But to do that, you have to increase the input cone tip resistance in the lower formation, in the lower fissure formation, by a factor of at least 3 compared to what we had at WP, if you use the Almen-Amri method. So to try to find out what happened, we mobilized a jackup rig. You can see it here, and it drilled 3 boreholes, 1 inch inside of refused pile P7 and P8, and 1 outside. What it found is no unusual soil conditions. There were no cemented layer, no boulders, which is what some of us had speculated. We encountered very dense sand and very hard clays, as expected. However, we did core through the wall of the Valhall pile. So you don't see that every day in a soil boring, fortunately. But that was the first irrefutable evidence that the piles had buckled. So you can clean the pile, you can send a downhole sonar, and you can generate the shape, the geometry of the pile. So for pile P7, you see the cross-section was heavily deformed in the bottom 4 diameter, with evidence of buckling as high as 8 diameter from the tip. P8, interestingly, buckled in a different manner. the cross-section remained intact almost all the way down to the tip. And based on video camera evidence, we know that it buckled only inwardly, only in the last half a diameter. So it's a lot of fun. You can see what it looks like going down pile 7. So the top of the pile is not buckled, there's no deformation. But once you start getting 8 diameters above the tip here, you can see some evidence of buckling, and then you go down the pile, and then 4 diameters right here, that's where it starts to be very heavily deformed. So it's not the soil. The difference between WP and IP is not the soil. So maybe it's the pile structural design. So you can see here the wall thickness schedule for the WP pile. Very simple, 3 wall thickness sections, flat tip, which was standard design for Amoco in the North Sea in the 90s. By contrast, IP had a very optimized wall thickness section with 9 wall thickness sections. The wall thickness goes up and down and up and down. And critically, it had a steep external chamfer of 76 degrees. So those are the structural differences between the 2 piles. And we asked ourselves, well, it's not the first time pile refused in the North Sea, so let's look at the database of what happened. So we put together a database of all the platforms that had been installed at the time in 2003 in the North Sea. And we found 188 platforms, 72 of them with piles, mostly in dense sand. And we found that the strong external chamfer was actually used in 40% of the platform. But actually in the Norwegian sector, it's almost 2 out of 3 platforms that had strong external chamfers. So if you look at the database and you plot the depth below the seafloor and the diameter to wall thickness ratio, the D/T, you get this scatter plot here. The green data is for the piles that did not refuse, and the red data is for the piles that refused, and you can see the Valhall case here. So the D/T for Valhall is well within industry practice, and D/T has nothing to do with the probability of refusing a pile. You can refuse a pile with a D/T as low as 20. D/T has more to do with fatigue considerations rather than refusal and buckling considerations. So how do you make sense of all these data? Well, you have to sort it by chamfer, and that's where things become very clear. If you look at platform with strong external chamfer, we had 16 platforms in our database. 5 platforms had at least 1 pile that refused, which is 31%. If you had a weak chamfer, out of 20 platforms, 3 had at least 1 pile that refused, 15%. Even with a flat tip, out of 35 platforms, you had 3 that had 1 pile that refused, still 10%. So this is perhaps the most important table of the lecture. This was an eye-opening, a watershed moment for the project, because in those days, nobody in the industry realized the correlation between using an external chamfer and the increased occurrence of pile refusal. So you might ask yourself, why use an external chamfer in the first place anyway? Well, in 2003, you can see the reasons that were invoked by designers. You used the chamfer to aid pile stabbing into the pile sleeve, to preserve pile verticality when you had sloping strata, to ease penetration in dense soil compared to a flat tip, or to reduce the risk of plugging by moving more of the soil on the outside than the inside of the pile. However, we had very experienced pile installers in the investigation team, and they said, we cannot corroborate any of those theoretical advantages based on our decades of installation. So none of the theoretical advantage could be actually proven in the field. So we had established correlation between a chamfer and risk of pile refusal now and pile buckling, and now we asked ourselves, could we establish causation? So we did numerical analysis, and the first method that we used was the one that would eventually be published by Aldridge et al. In 2005. The math is in the paper, but you can assume a size of defect, and you can calculate the cone tip resistance at which the yielding of the pile will start. And for our problem, we calculated 113 MPa. We also did a lot of finite element analysis using a variety of software, Abacus, LS-DYNA, Plaxis, ICFEP, and they all showed the same thing. At the tip of the pile, you had a strong stress imbalance if you had a chamfer. And this stress imbalance, P here, and you see fractions of P's, they are proportional to the cone resistance. This stress imbalance was not seen when we had a flat square tip. So you can see an example of buckling patterns, and perhaps that's what happened in pile 8, where you have internal buckling during the half diameters of the pile. But maybe the pressure around the perimeter of the pile is not uniform. Maybe you have a sloping strata. So if you double the resistance on half the perimeter, then you get a different buckling pattern, and you can calculate cone resistance somewhere between 105 and 70 MPa that would cause the pile to start yielding. Here is another analysis using Abacus and the Basel user element. You can see how the stress imbalance is modeled. We calculated 90 MPa to cause the pile to yield. And you can see here in this simulation, when the pile is at 50 meters, the analysis predicts yielding here. The area in gray is above yield over 4.3 diameters, which is reasonable based on the images that I showed you from the downhole sonar. You can also track how the pile deforms as it enters various strata. So you start here with a little difference in the diameter, so a little bit of an ovality, and this red line tracks how much this red point goes down, and this blue line tracks how much this blue point goes out. So the cross-section flattens in the sand, and then it kind of stays stable in the interbedded sands and clays, and once you get to the deeper sands, that's when really the cross-section flattens and the pile refuses. So all of those analyses are fairly consistent with the observations that we had. So what are the causes of the IP pile refusal and buckling? So as often in those cases, you have two sides. You have two independent panels. There you have two versions of the truth, two versions of what happened. But we set up two investigation panels in a Delphi-type situation, which means that every so often, every few months, those two panels had to meet, and each panel had to listen to the arguments and the conclusions to date of the other panel, and they had to figure out what it meant for their own investigation. And the goal is to obtain consensus between those two panels, which I'm happy to report we did get in the end. So not in order of importance, but that's kind of the recipe for a perfect storm. You need a steeply chamfered pile tip, a sand layer of sufficient density and stiffness, a sand layer of sufficient thickness, and an initial defect, an out-of-roundness or a pile deformation when you enter the very dense sand. Now, it's fair to mention that in all those numerical analyses, those pretty diagrams I showed you, to get there, we had to put initial defects that were larger than what we measured on the piles. All those piles were manufactured within code tolerances. On the other hand, all the analyses that we did were static analysis. Then they don't capture the dynamic aspect of pile driving. So maybe we have compensating assumptions in our analysis. In any case, we learned the lesson, and now if you read the ISO code, you'll see this statement here. The pile of the tip or the driving shoe should be flat or beveled towards the inside of the pile. The pile tip and driving shoes with bevels toward the outside of the pile shall not be used when driving through dense and very dense sand, as they have been shown to be a contributing factor in observed pile buckling. So if you read the code, and if you wonder why this shall statement is there, now you know. And if you choose to ignore it because you don't have to follow ISO, well, you know, caveat emptor, as the Romans used to say, buyers beware, you know. So how did we remedy the situation? We installed what's called a piggyback system. So you can see here we installed two insert pile in the piles that had buckled to get the right wall thickness in the right elevation. And we added one more pile through a pile sleeve at each of the corners. And you can see the top sides being successfully installed on the platform with a 1-year delay. So when came time to design the next platform, do you think we took a few saw borings with modern techniques? Yes, we did. So here are all the CPT records from the 2004 site investigation. So even with modern techniques, we still refused at 120, 130, 140 MPa. So we have extremely dense sand, very shallow. If you recall, I told you that we calculated a cone resistance somewhere between 70 and 113 APA to start yielding the pile. So yes, it is possible that as the basal analysis showed, the pile may have started to buckle, to yield and buckle in the upper sand, and then finally refused in the lower sand. But it's interesting to see the difference in assumptions that you have to make to predict the right SRD. This is the flat tip, this is the high bevel, and it's the same sand in the two locations. So this was the story of the Valhall pile buckling in all the gory details. So now you can't say you didn't know. We're going to pivot now and talk about the scientific method, at least according to Professor Richard Feynman, Nobel Prize winner in physics in 1965. According to him, it involves 3 steps. You develop or you guess the theory, you compute the consequences of the theory, and then you compare those consequences to experiment. So for us, that means we develop foundation design methods, we predict the field performance of the structure and the foundation, and then you compare with post-event observations. And tonight we'll compare with post-hurricane observations. Can you prove a theory wrong? Yes. If the results of the experiment disagree with the predictions of the theory, doesn't matter what your name is, doesn't matter how pretty your equations are, the theory is wrong. The question is, can you prove a theory right? Let's see what Professor Feynman's perspective is on this particular point.
Suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simple.
Okay. To do justice, I'm going to start the video again. Oops, if I can.
Suppose that you invent a good guess, suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simply not proved wrong. Because in the future, there could be a wider range of experiments, you can compute a wider range of consequences, and you may discover then that the thing is wrong.
So, if you adopt this point of view, it makes you, which I have, it makes you very humble, because you can never be sure that you are right. You can only be sure that you are wrong. So through the rest of the lecture, I will walk you through some case histories that show you that the design methods that we have now in our codes and standards, if you use the latest one, they have not been proved wrong by the performance of offshore foundations under hurricane loads. So we will start looking at floating rigs and mooring anchors. You can see here in the year 2000s, there were a variety of hurricanes that came through the Gulf of Mexico. And in particular for Katrina, this was the first time that drilling rigs were subjected to Category 5 hurricanes. And you can see that each of those hurricanes caused mooring to fail. In particular, for Hurricane Ivan, you can see the path of the eye of the hurricane that went right over Mississippi Canyon Block 383, where the Jim Thompson drilling rig was drilling. Our hindcast analysis showed that when the mooring began to fail, the return period of the waves was somewhere between 100 to 1,000 years. So huge waves. And in those days, you only had to design to a 10-year event for mobile temporary mooring system. So you would expect some mooring lines to fail, which they did. All of the mooring lines failed. 5 of them failed within the wire itself or at the fair lead. However, which is what we would expect, because this at the fair lead is where the line tension is the maximum. However, you can see that 4 lines broke at the suction pile at the pad eye. So you can see a picture of all those broken pad eyes. This anchor here, you have the pad eye that is bent, but you can see this pad here, the pad eye is missing, pad eye is missing, pad eye is missing, and the pad eye is missing. So you see, when those pad eye break structurally, they just snap right off. Can we explain this performance? Does it make sense? Is it consistent with our predictions of the theory? So what you can do is, if you look at inline loading first, you can develop interaction diagrams with the vertical ultimate load and the horizontal limit load as a function of various adhesion factors. So you can see those diagrams here. And you also have to put the breaking strength of the mooring line. So the load cannot exceed the breaking strength in any direction. Remember, those suction anchors are not designed for a particular location. They must be able to work all around the Gulf of Mexico, so they're designed for low estimate soil properties. And then you do the hindcast, you do the time domain analysis, and for the line 3 and 5, which broke in the wire, you can see that, yeah, the load will reach the breaking strength of the wire before it reaches the capacity of the anchor. So it makes sense that the line breaks and the anchor does not pull out of the ground. Now, you can also look at out-of-plane loading, and you can draw this interaction diagram. You have the line tension, so the line tension cannot be more than the breaking strength of the wire. And then you have the geotechnical torsional capacity using adhesion factor of 0.75 and 0.55. So this is the range of torsional capacity of the anchor geotechnically. And then you do the time domain analysis, and for the 4 lines that broke at the pad eye, the end of the arrow is when the pad eye breaks. At every step of the analysis, you have to do a finite element analysis of the pad eye, and when you calculate the stresses above yield, you say, well, that's when the pad eye breaks. So you can see first, it makes sense that the line didn't break because none of those loads reached the breaking strength of the wire. And some of those anchors rotated, some did not rotate, which tells us that the torsional capacity of the anchor was pretty close to the structural capacity of the pad eye. So whether there was rotation or not, it's tough to tell. But overall, the results are, we can explain this with our design methods. Another type of anchor that was put to the test is the OmniMax anchor. It's a gravity-installed anchor. It is deployed, and the mooring line, the deployment line is severed, and the anchor self-embeds into the seabed under gravity. So you can see what it looks like. It has a swiveling mooring arm, so in theory, the capacity of the anchor is independent of the azimuth of the load. And by playing with the top fin and the bottom fin area, you can ensure that the anchor will dive when it's loaded beyond its capacity. That's the theory. And during the development of the anchor, there were tests done in Laponite, and you can see that as you increase the load, the anchor keys itself perpendicular to the load, and the load attachment point dives deeper. That's the theory. So there was one rig that was moored with OmniMax anchors, and during Hurricane Gustav, all the mooring line broke except for one line. So with the hindcast analysis, we estimate that the anchors were overloaded, the load over the capacity, by about 40%, 40 to 44%. And we know the embedment before the hurricane and after the hurricane when we retrieve the anchor. So you can see that under the hurricane loads, the anchor embedded an additional 1 to 2 anchor length. This is what we would expect from the theory. In particular, you can see that line 5 was overloaded, did embed a little bit more, but it did retain enough capacity to not break even after experiencing a rotation of 165 degrees. So, in summary, for a floating system and anchors, the design methods have not been proved wrong. Most mooring failures occur in the waterline, which is what we want, which is what we intend. For suction anchors, we can predict where the line fails, or the anchor fails structurally, or the anchor fails geotechnically. And we haven't seen that yet. We have seen no geotechnical failures yet, but we can explain that. For the OmniMax, yes, it does seem like the anchor dives when it's overloaded, and yes, it does seem like the anchor retains its capacity even after huge rotation and out-of-plane loading. So really, out-of-plane loading based on field performance is where the weak link is, and if you want to improve the performance of anchors, you really need to concentrate on the A, geotechnical, and B, structural capacity under very large out-of-plane loads. Now we're going to look at the performance of fixed structures. So oil and gas activities started in the Gulf of Mexico in 1948, and since then 300 platforms have been destroyed by hurricanes. There were 60 fixed structures destroyed just in 2008 and 59 in just one hurricane here, Hurricane Ike, and you can see all those red dots on the continental shelf. What did we learn? So when we say destroyed platform, either the platform is laying on the seafloor and with the foundation most of the time intact, or it's damaged beyond repair with severely buckled members, or it's leaning at the waterline beyond repair. So all those three structures would be called destroyed. So we funded a study with API, and I'm going to show you two case records. The first one is a freestanding caisson that was damaged during Hurricane Andrew, and it's a very simple structure. You have one conductor, one pile, 29 meters into soft clays, and very shallow water depth. And it was found leaning 15 degrees at the waterline. So this is an example of what the caisson looked like. It's not the actual caisson, but you can see the typical damages after hurricanes. So we developed two structural models identical in all parts except for the lateral pile-soil interaction, the so-called PY curves. So the curves here from ISO 2016, monotonic curves, these are the API curves we heard about today, the Matlock curves, and those new curves that were published in ISO earlier this year, we used the cyclic curves, which are stiffer and stronger than the monotonic curves. So two different structural models. So you can do dynamic pushover analysis, and to derive those curves, you have to use the DSS shear strengths. That is the shear strength measured under direct simple shear. That's now in ISO. So you can see the time domain analysis. The wave comes and submerges the topsides because we're in such shallow water. With the old curve, you can see very early formation of a plastic hinge, and you don't see too much yielding in the pile because the PY curves are so soft they can't mobilize any stresses in the pile. With the new curves, you see the plastic hinges slightly higher, and you can see much more yielding in the pile because the PY curves are stronger and they can mobilize stresses in the pile. And obviously, the caisson leans less with the new curves. At the end of the simulation, this is what you predict. You predict a final leaning angle of 34 degrees using the old API Matlock curves, and you predict 16 degrees using the new 2025 ISO curves, and the field observation was 15 degrees. So the new design method, again, has not been proved wrong with the performance of this caisson. Now, here's another case record, the second case record. This is a jacket in the Ship Shoal area that was damaged during Hurricane Ike. Again, we're lucky. It's very simple structure. There's no conductor, so 1 pile per corner. Again, 55 meters into soft and stiff clays. And the original structure was the one damaged. So what kind of damage did we see? Well, close to the water line, we saw joint failures and separated members. A little further down the jacket, you can see buckled braces. You can see the bowed shape of those struts. So they buckled under compression load during the event. And a little further down, you can see joint that cracked and were damaged under compression loads. And very importantly for us geotechnical engineers, for the foundation, there were no indication of pile foundation failure or even lateral displacement in any of the underwater inspections. So you can do the same thing as before. You can generate 2 structural models, similar in all aspects except for the PY curves. With the old curves, the old API curves, you see a lot of plastic hinging, and you see some 2 buckled struts. With the new curves, to 2025 curves, you see no hinging, a little bit of yield, and more damage into the jacket itself, and that's very typical. With the new curves, you will predict less pile damage, more damage in the structural truss. If you look at the pile head lateral displacement during the event, with the new curves, after 2 cycles, you predict maybe 0.1 meter of permanent displacement. With the old curves, you predict 0.4. So what we say is the hindcast with the new 2025 curve, cyclic curve, is more consistent with the fact that we actually couldn't see anything in the underwater inspections. So there's a difference in the predicted structural performance. The new curve predicts this member to be buckled, and the old curves do not. So did it buckle? Yes. So this buckled member that is only predicted with the new PY curves, here it is. That's proof. There's no arguing. And additionally, the fact that there's no yield, no plastic hinging, and very little yield in the pile, again, is consistent with the fact that there were no measurable displacement at the pile head. So again, what we say is that the new design methods have not been proved wrong with the performance and of those jackets post-hurricane, and we are able to match damage that we can actually observe. So it is really of the utmost importance to identify the right failure mechanism, because if the jacket is not fit for purpose, if you have to retrofit it, if you have to repair it, you will send divers into the water with non-trivial HSSE risks. So we owe it to all those people that whatever repair and strengthening they do is meaningful and impactful. Now, in closing, I will say that I'm aware that all those lessons were learned during the production of hydrocarbons, but I trust you will agree with me that they are transferable to new energy projects. The structures are the same, the type of structures are the same. Yes, the scale varies. The number of structures that we put varies. Yes, there are differences between a freestanding caisson and a monopile. So I didn't say blindly apply the oil and gas lessons learned to offshore wind. I say they are transferable. And with this, I thank you for being here tonight.